So we have started discussing projective space Pn and have defined the notion of a projective variety X inside there, both as a set and then as a topological space. And you know the drill by now. The next thing that we need to do is define a sheaf of regular functions. Once we have this, X with this sheaf is a ringed space. And then in this chapter here, we're first going to show it is a pre-variety. This happens in this video here. And then we're going to check actually has these nice properties of being a variety. Okay. And so we need to define regular functions when X is an affine variety and U is an open subset. Then we know a regular function means that locally it is given as the quotient of two polynomials. So as the quotient of two elements in this coordinate ring A of X. Now, when X is projective, then we have this homogeneous coordinate ring S of X. But the problem is, for arbitrary G and X, it still doesn't make sense to write G of X divided by F of X as a function on X. To see that, well, you can take G to be X0 squared, F to be X1 for functions in two variables. And then if you take this quotient here, well, you could evaluate at the point 1, 1, then you get 1 squared divided by 1 is 1. Or you could evaluate at 2, 2, then you have 2 squared divided by 2 is 2. So you see you don't get the same number. And so since the point 1, 1 and point 2, 2 inside P1 are the same point, well, you wouldn't get a well-defined function on an open subset of P1. But of course, here you see what goes wrong is that the numerator and the denominator don't have the same degree. And so when you scale, you get a global scalar out. Once you fix this, once you require them to be of the same degree, this actually works. You get a well-defined function. And this is exactly how we're going to define regular functions on projective varieties. So if X is projective variety and U in X open, then we say a function phi from U to K is a regular function if it satisfies the condition for all A in U, there exists D in N, and then Fg homogeneous of degree D, of the same degree D, such that f of A should not be 0, the denominator, and then you define phi to be phi of X equals G of X divided by f of X, and you want that this condition holds for all X inside some neighborhood of A. So some open subset inside X. So this is the local form of regular functions. And then we write O X U for the set of regular functions on U. The first thing, now we have just defined it as a set of functions, and we should check that it's indeed a K algebra. That's not super hard, but I mean, there is something to check here. Namely, well, let's say you have all these Fi and Fj and Gj as above, and you had a regular function, g1 divided by f1, and another regular function, g2 divided by f2, at least locally around some point. Let's say you want to add them. Well, you just add them as you're used to. You get this expression here. And then you see if the gi and fi and so on were of degrees d1 and d2, then, well, this here is of degree d1 plus d2, and this here also both terms of the same degree. So you still get a quotient of homogeneous polynomials of the same degree. So this is still a regular function, and similar, maybe even easier for the multiplication. And you can also multiply by elements in K. So this is indeed a K algebra. The second thing is that this condition on regular functions is local. We always ask for any point in here, we have a local form. And then there you might also know the drill by now. Once you have a set of functions on these open sets U satisfying a local condition, then this satisfies this sheaf axiom. You can check if something is a section of this sheaf on an open cover. And so we indeed get OX having the structure of a sheaf on X. And so this means that when X is projective variety, then we get a ringed space XOX like this. And then what we're going to do in this video here is check that this is indeed a pre-variety. So we need to find a cover by affine varieties. And the idea is, as before, that somehow Pn has this affine cover by u0 up to un by copies of the affine space An. And then X sits inside here. And then you hope that if you just intersect with these affine things, well, you will probably get some closed subsets of these affine varieties. And then these should have the structure of the affine varieties that you're used to. And this is basically the content of this next proposition. So if X inside Pn is a projective variety, then define Ui. Let's not define it for all of Pn. Actually, we can just define it as the points inside X, such that Xi is not equal to 0. These are clearly open subsets of X. And the claim is that these, together with the restrictions of the sheaf we just defined, are affine varieties for I equals 0 to n. In particular, we have covered X by these affine varieties, so X is a pre-variety. And so the proof by symmetry, it suffices that we just check the case I equals 0, the other coordinates are similar. And then let's give everything names. So let's say X is the projective vanishing locus of an homogeneous ideal J. And we define Y to be the affine vanishing locus of the dehomogenization of this inside An. So this should be the part U0 of this variety X. And the claim now is that this is exactly true, that somehow you can write down the explicit map from this affine vanishing locus to this open subset U0 above, taking these inhomogeneous coordinates and homogenizing them like this. And the claim is that this here is an isomorphism with inverse given by the thing that we know, that somehow you take these quotients here. So you're allowed, of course, to divide by x0 because you required it not to be 0. So this is a well-defined map in the other direction. Okay. And here somehow the important thing is that we don't just have to check that this is the map of sets, but we have to check that this is a map which respects the rings on both sides. So here Y is an affine variety, so it has a ring OY that we define. And U0 is an open subset of this projective variety, so it has this sheaf of rings, which is just a restriction of OX defined above. And so we really need to check that it's an isomorphism with respect to these structures of ring spaces. Once we have this claim, I claim that this finishes the proof because then we see these U0s are isomorphic to affine varieties, and so we have a cover by affine varieties. This shows that X is a pre-variety. Okay. Now the first thing is, so let's work our way through the structures that we have to show here. One thing is that these are well-defined maps. This follows from these standard things that if you have something in the affine vanishing locus of J, the inhomogenization, it maps under this map to the projective vanishing locus of J, and vice versa. These are well-defined maps of sets, and they are an inverse pair. Somehow, if you compose them in the two directions, you get an isomorphism, or you get back the identity on both sides. So on a level of sets, we have shown these are inverse bijections. Then next level, they're both continuous. For this, we have to compute the inverse of a closed set in U0. A closed set on U0 is some projective vanishing locus intersected U0. And then if you take the inverse under this map, well, you just get the affine vanishing locus inside Y of this inhomogenization of this ideal. And so this was done in some remark. And then similarly in the other direction, if you take F of some affine vanishing locus, then you exactly get this projective vanishing locus here intersected U0. So the correspondence between the closed sets on one side and the other side is just the usual correspondence between closed sets in projective space and in these affine patches. So we have an isomorphism of topological spaces. And so now we can finally check that regular functions pull back to regular functions, the final part. So, and we do this in both directions. So let's say phi is a regular function on an open subset of U0. So locally, it looks like the quotient of homogeneous polynomials of the same degree. Then, well, this map F, I mean, if we look at it again, the map F just plugs in x0 equals 1. And what this does to this polynomial, setting x0 equals 1, was just the definition of this dehomogenization. And so this pullback here is just the quotient of the dehomogenizations. This is the quotient of polynomials, and so is regular on Y. So pullback in one direction works, and then the pullback in the other direction, let's say phi is now a regular on open subset of Y. So it's locally the quotient of two polynomials. And then this F inverse here, what it does is it plugs in xi, it replaces it by these functions xi divided by x0, like this. So we get this here just plugging in the definition. And now we want to write this as the quotient of two homogeneous polynomials. A priori, these here would be rational functions. And so we have to clear their denominators. And we can do this just by multiplying by the same sufficiently large power of x0. So we can take x0 to the e, where e is the maximum of the degrees of f and g. This suffices. And then you can check, well, this is basically, this almost looks like the homogenization of g and the homogenization of f, except it might be that we take a bit more of the x0 than we need. So it might be a product of x0 to some smaller power times the homogenization. But in any case, I mean, what you can check is that both of these numerator and denominator are homogeneous polynomials of the same degree e, and that's good enough for us. So this shows that this is exactly the form of a regular function on this projective variety, and so this is a regular function. Okay. So they pull back regular functions correctly in both directions. So they're both morphisms of ring spaces, and then since they're also inverse to each other as maps of sets, they're inverse morphisms. And so this proves the isomorphism that we wanted, and this finishes the claim, and this finishes the proof. Okay. So what we basically just did here is we checked our new fancy definition of regular functions on projective varieties is compatible with the old definition that we had before. And then as a final exercise for you, there's some more compatibility checks. So we always have to make sure that our new constructions fit together with what we discussed before. So first of all, if you remember, when we did pre-varieties, we had this gluing construction, and our great example was that we glued together something which we called P1 back then from two copies of A1. And what you can check is that that P1, which we constructed kind of by hand, is just the same pre-variety as the pre-variety P1 that, this here was the one that we had from gluing. And then above, we defined the new structure of pre-variety on projective space P1, and you can check these are the same structure. So that's one small compatibility check. And then the other thing is, well, let's say we have X inside Pn, a projective variety, then we have just defined a notion of pre-variety on X. On the other hand, well, of course, we then also get a pre-variety structure on Pn. And X is the closed subset of this pre-variety. And so we get the structure of a closed I should write here sub pre-variety on X, right? If you have a pre-variety and a closed subset, we get another structure of a pre-variety here. And again, so we are now in this position that on X we have two structures of pre-varieties, and the exercise would be to check these are actually compatible. These give the same structure like this. So everything that we did so far fits together nicely, and no matter how you try to put structure of a pre-variety on X, you'd always get the same thing. Okay, and then next we're starting to approach the problem of how do we show that this pre-variety structure is actually a variety.